Got it? Okay. So from yesterday, you got theta, omega, alpha. Theta measures your radians. That's equivalent to like a linear distance of meters. Omega is your rate. That's radians per second, which is equivalent to meters per second. And then you have alpha, which is in radians per second squared, which is equivalent to meters per second squared. And then you've got those three crossover equations that D equals R theta, D equals R butt, A equals R fish, okay? So let me kind of give you some hints. That answer for number 4, the angular velocity of the Earth as it spins on its axis, okay? So when you're talking about angular velocity, that's in radians per second. So here's this strange rock that we're on. How many hours does it take for it to make one revolution? 24 hours. How many radians is it going to move through? 2 pi. So take 2 pi, divide that by 24 hours into seconds. So that answer to number 4 should be something times 10 to the negative 5th. Okay? So that's how fast all of us are moving. So this is the great equalizer. So whether you are at the equator, or if you're up here in Mesoamerica, or if you're in Greenland, doesn't make any difference. We're all spinning at that number of radians per second, okay? Because we all take 24 hours to make one revolution. It isn't like, oh, the equator takes 24, and up here in Maze it only takes us 22, okay? We all spin at the same number of radians per second. Now, what changes is that answer to number 5. It says, what's the linear velocity of the person standing at the equator? So you've got the radius of the Earth. So if you're at the equator, you're moving faster in a linear sense than if you're standing up here away from the equator. So this is why when you go to launch vehicles into space, this is why you want to launch, like for example, the United States, we launched in Florida, okay? The reason that we launched in Florida is because that's close to the equator. Because basically what we're doing by launching at the equator, we're getting an initial velocity because of the rate of spin of the Earth, okay? So right now they're getting ready to launch the Webb telescope, and they basically moved that down to the equator. So now companies are launching from the equator because that's your maximum rate of spin in terms of gaining a tangential velocity. So basically you're getting a free initial velocity that you don't have to get with rocket engines. The most expensive place to launch rockets is from the poles, because then you don't get any tangential velocity because of the rate of spin of the Earth. So that's why it's really difficult to launch things from the poles to get them into orbit, because you don't get any basically free velocity from the rate of spin of the Earth. Okay. So that answer to number 5 should be faster than the speed of sound. Okay? 343 meters per second. Okay? Now on number 6, some of you had come in and asked about number 6. So let's make sure everybody's cool with that. So you've got George over here, you got Joe over here. So this is going to be the mass of George, which is 56 kilograms, times G. And then you've got Joe, which is what, 43 kilograms, times G. Now, with this one, you can put the fulcrum anywhere that you want. I suppose you guys want to be able to see what I'm writing.
Nope.
That's all right.
Why did you guys wait this long to tell me? I mean, I've been
I didn't even
writing.
realize.
I wasn't paying attention.
Oh, that makes me feel good.
Figuring out number 3.
I can't believe it.
I'm sorry.
I'm trying to see what you
It's not
3 is
I'm on a
dumb.
different level.
Book 3.
Number
Wait, so
textbook
what's
3
seven?
is
Justin, I
dumb.
understand
Number
it now.
textbook. Would you just take, what was it by minus 7?
Yes.
Hmm?
Oh, no,
Number 1.
Oh,
Smaller is holding my money.
You don't sound like you're in a very good mood right
well, I hate technology at times.
now. That's facts.
We have technology.
Why did my chalkboard green?
Technology is kind of weird sometimes.
Just smack the computer against the desk.
Yeah, it is.
Very hard.
Battery.
Yeah.
Huh?
Percussive maintenance, just to say.
Ah, yes, percussive maintenance. It always works. Children, you need to fix them up. Percussive maintenance. TVs,
What?
percussive maintenance.
Tell me, Justin, the reason you are the way you are is because your parents are cussing.
Actually, I used it on myself. I was like, I need to
Okay,
solve a way
now
to
we're
get out of
back.
this crib. Percussive maintenance.
When in doubt, unplug it and start back. Okay, anyway, so those are your three equivalents, okay? Meters, meters per second, meters per second squared. Your three crossover equations. And then here's this question on number 6. So you can put the fulcrum anywhere that you want. So here's your two options how you can work this problem. One option is that you just do like a guess and check kind of thing. So you know the entire length of this thing is 1.75 meters. So one option, and here's the whole idea, is that the torque of George is going to equal the torque of Joe. So one option is you take 56 kilograms times G times some distance. Let's say I'm going to guess 0.25 meters. Okay, that's an option. Okay, because is the fulcrum going to be closer to George or closer to Joe? Because he weighs more, right?
Less for you.
So you could let that be 0.25 meters. So this is going to be 43 kilograms times G. Now, what would Joe's distance be?
Greater than George's.
Well, if the total length is 1.75,
Total length minus.
and this is 0.25, how much is left over?
1.75 minus 0.2.
Yeah, so 1.5, right? So that's an
That's not
option.
the answer.
And you try this, okay, and you see, hey, are these two numbers the same? And then if it isn't, then you adjust accordingly. It's a long, arduous process. It works, okay? Guess and check. It works,
That would take a lot longer.
okay? Now, then you can say, oh, algebra to the rescue. Now, here's one thing. If you set this up right away, what's going to happen to G if you wanted to? You could actually just drop G out,
Thanks for nothing.
okay?
Oh, I just turned it into
If you wanted to, you could. You're still going to get the same answer.
Okay.
So one option is that you let the distance to George be x, okay? Then what's left over?
1.75 minus x.
1.75 minus x. So then you'd have 56x is going to equal 43, and then you distribute the 1.75, it turns into an algebra problem.
It's not that hard.
Okay? Get all your x's on one side, get all your numbers on the other. So your distance to Joe should be about 1 meter. Okay? And here's how you can check that you got it right.
Very close to one.
Take your distance to Joe, multiply it by her weight,
See if they're equal.
see if that equals the other distance left over multiplied by George's weight, and see if the two numbers balance out. If they do, hey, you did it right. If they don't, you didn't. So this is why if you ever watch like truck commercials, it'll say so, because the equivalent in the English system is foot-pounds. So it'll say, oh, the Dodge has so many foot-pounds of torque, okay? And that's what they're talking about, is that how much torque can that engine generate. Anyway, on number 8 and 9, every answer on 8 and 9 should be between 100 and 150.
Yes.
Excuse me, between 100
Wait,
and 160.
even the revolutions?
Yeah.
Oh. I
See,
definitely
the
did not
first
do
time I
that.
did it, I did it like a 6
I did not do that right then.
Now, let's talk about number 8. Okay? So, that omega time graph should look something like this. So one option is that if you're into geometry, one option is that you find this area underneath this graph. That's going to be in radians. Convert that into revolutions. Okay, that's an option. If you're into equations, you could use theta equals 1/2 alpha t squared plus but not time. Okay? You could use that if you wanted to. Really doesn't make any difference. So, but no matter what you cannot do is you cannot take your velocity times time and go, oh, there's theta. Why can't you take omega times time to get theta on number 8?
It's not constant.
Huh?
It's not constant.
Yeah, it's not constant, okay? You're speeding this thing up, right? So that's why you can't do that. On number 10, if your time is wrong, everything else is going to be a train wreck. So your answer to number 10 on that time should be between 5 and 8 seconds.
5 and 8. Oh, I did this one too.
What do you mean?
Oh,
What do you have as your time?
I have 3.
Oh, God, no.
182.
Yeah, that's a lot worse
No.
than 30.
You get that?
Okay.
I had 3.
It's just the
Do you want me to go over number 3 out of the book, or have you all sorted that out?
I figured it. I don't know about other
Let's
people.
go
I
over
really
it
didn't figure that
because
out.
it's John.
Okay. So we'll do a little demo.
That's just algebra. So you were right.
So here's what you've got. So if you look on that first one on A, so you've got a larger mass because yes, the blocks are different sizes. So you've got a large, so these are kind of like Atwood machines, okay? So I've got like a 500 gram mass on one side, okay? So here's the deal. Is this going to create a torque on that wheel?
Yes.
Yes, right? So if you look at what's happening on this first one on A, which direction is the heavier mass moving?
I forgot.
Well, if you look, so here's your setup. Here's the diagram that you've got. So you've got a larger block, and then down here you've got a smaller block, and you're told that this one is moving up, and this one is moving down, right? So if that's the case, right, so it's just like this. So this one is, when I let go of this one's moving up, right? So it'd be like this. Now, when that happens, as soon as I let go of it, what's going to happen? What's going to happen to that larger mass? It's going to apply torque, right? Okay? So it's just like this. So imagine this is what's happening when I let go of it. So I'm like this. So as soon as I let go of it, what does that larger mass start to do?
It just accelerates.
So that larger mass is going to start to slow down. What's the smaller mass going to start to do? It's going to
Speed up.
speed up. Okay, so we're going to be going like this, right? So they're both, you can't have one speeding up and the other one like slowing down. So they have to be going like in conjunction. So you're like this. So visualize what's going to happen. So, and then look at what's going to go. Now on B, you're like this, and we're just going to let go. Okay? So that's already moving. So since that's already falling, that's just going to keep falling, and that one's just going to speed up even more. So this is what you've got to be able to visualize in terms of what's going to be happening. All right. So
Fine.
on number 3, okay? Number 3. So make sure that you tell me what is what. So on number 3, let me give you a hint. Do not just go plus minus and think I'm going to know what that means, all right? if you want to make up a column and go, oh, here's my angular velocity and here's my acceleration, that's cool, okay? But do not just put positive and negative and think, I'm going to know what that means, right? You tell me, oh, this is my angular velocity, this is my acceleration, okay? Do not just put those and assume I know what's going to happen. All right. Anything else? Going once, going twice. Adam. Which one? Out of the book or out off mine? Okay.
Fine, I relent. We're both wrong. Good try.
It says to find that, you just do d, which is distance, divided by the radius, and then you find.
But if it's circumference, it's already in radians.
It's in
not?
meters.
So you just use initial velocity.
It's in meters.
Then you
So
get
it's
the right
75.4 radius. I need 5 minutes.
If you order any of the clothing stuff, I need those orders by Friday. I don't necessarily need the money, but I do need the order.
This makes sense.
Okay, so here's the whole key to this, Adam. This door is hinged right here, okay? So when I apply that force to it in this direction, which direction is that door going to move? Is it going to move counterclockwise or is it going to move clockwise? Okay, so then, and that's what I told you on this one, counterclockwise is defined as positive, clockwise is defined as negative. So all those answers to A, B, C, D, and E are either positive or negative, depending upon which way it's going to spin. Anything else? Morgan, did you have a question?
Mine was on 5.
Okay. All right, anything else? Going once, going twice? So, and let's practice good stapling skills, shall we?
I didn't square my teeth. That makes no sense.
Let's practice good stapling skills.
Yeah,
All pages are able to be stapled together.
there we go. That's what I did wrong. I didn't squares. I did squares. And now we're finding the velocity, which is basically just acceleration times. So acceleration is 27.5. Or final velocity. Yes, 27.45.
Don't flip out, these are just equations.
Yeah. Carter's upset because he didn't have an equation for number seesaw.
Number seesaw.
Yeah, I can't think of it. That looks horrendous.
Like this?
I don't like that. Do we do engineering design?
What is the
IED? Oh yeah.
okay?
No, that was
How do you
Schmidt.
find that?
IED was
How do you
Schmidt.
find that?
I don't remember IED.
Oh, you divided by 2.
That was one of the things. Did you get to skip IED? No, we did robotics.
Oh, that's
IED.
good.
Oh, Devin? Devin deserves it.
Yeah, it goes this way.
A little worthless piece of art. To be fair, this guy is low. Not Donald.
That's the thing. Well, that's the thing you get.
I don't like that. MR squared is not thin radius of a hoop. I refuse that.
It takes 12 seconds.
Okay,
All zero.
so,
I don't get this.
Ray, did we stop that or is that still going?
It's still going.
Okay, we'll stop that. Just because it's easier to start, it's easier to do in small.
Parentheses.
All right, so if theoretically, at some point, if I ever do get to retire. And I could come back and give one lecture out of the fall class. This is a lecture I would come back and give, okay? And it does a whole bunch of kind of random things will, at the end, make a very nice, cohesive understanding. So, today's class is brought to you by the concept of moment of inertia. Now, it's related to inertia, but this is going to involve things that spin about an axis. Okay? Brady, did we start that back up? So, here's the deal. So, moment of inertia is a resistance to a change in angular velocity. So basically, and it's the same idea of inertia in that sense. So inertia is a resistance to a change in linear velocity. So something like an elephant. Oh, an elephant is really tough to get to move because it has a lot of mass. But once you get that elephant moving, it's really tough to get it to stop. Okay? So the same thing is true of moment of inertia. So if something has a large moment of inertia, it's tough to get it to start to spin. But once it's spinning, it's really hard to get it to change that angular velocity, okay? So like the Earth, for example, which is a good thing, our Earth has a pretty large moment of inertia. So that means a day is consistently 24 hours. Now, they've actually figured out that they think when the Earth was first formed, that a day was actually a lot shorter. It might have been like 18 hours. So the Earth is actually slowing down as we spin. Okay, and that's even happening down. Don't sit there and go, oh, I feel it slowing down. No.
Oh, boy,
Okay.
what I do.
Okay, and then thank God it's not. Okay, because if it was slowing down rapidly, then that's not going to end well for us. Because imagine if the Earth wasn't spinning on its axis at all. Yeah, so you'd either be in daylight or you'd be in darkness. Okay, and that would be it. Okay. And yeah, you could be in that transition line, but for the most part, one side of the Earth would be really, really hot, and one side would be really, really cold. And you'd have that borderline in between. So, and it's good that it spins at a constant rate. Hey, day is 24 hours. Yeah, is it technically slowing down just a tiny, 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 tiny bit? Yeah. But, so it's like a top, right? So when I get this top spinning, okay, that top has a certain moment of inertia, okay? So once I get it to spin, it wants to keep spinning. There's a little bit of friction, so it's going to slow down a little bit. Now, obviously, if I apply a lot of force to it, oh, that's going to make it slow down even more. So when you talk about moment of inertia, it's represented by the letter I, okay? Now, here's the other thing that makes inertia different from moment of inertia. Moment of inertia is based upon different mathematical formulas. Inertia itself is just mass. Oh, 1 kilogram versus 5 kilograms, okay? 5 kilograms is always going to have more inertia than 1 kilogram. Moment of inertia, though, is dependent upon two things. It's dependent upon mass, and it's also dependent upon where that mass is located. Now, this I equals mr squared, this is the simplest form of moment of inertia, okay? This is like the center tree, and we branch out different formulas from this. This I equals mr squared can only be used in two situations. Where you have like a point mass, in other words, like if I take the, where's my rubber stopper? Okay, so like if I take this rubber stopper and swing this thing around like this thing has a certain moment of inertia. It's traveling in a circle, okay? It's revolving around my hand. The moon has a moment of inertia because the moon is going around in a circle, okay? The Earth has a moment of inertia because it's a point mass going around the sun. The other time you can use it is this, and this is what's on that equation sheet that I just gave you. Do not memorize these. If you need any formulas for moment of inertia, I will give them to you. Okay? So don't memorize these. If you need them on the test, I will give you these equations. You just have to know how to use them. But what you'll notice is they all have a variation on the theme of mr squared. So mr squared is kind of get us this idea. There's variations on it, but they all have mass times some radius squared. So what are the units for moment of inertia then? Well, that mass is going to be in kilograms. The radius is going to be in, and that's going to get squared. Now, there's no cute way to do this, okay? Moment of inertia is just kilogram meter squared. And no matter what the object is, when you look at it, they all have the same moment of inertia, okay, in terms of units. Now, some are 1/2 mr squared. Some is 1/2 r1 squared plus r2 squared, okay? But they all end up with the same units of kilograms meter squared. Okay, so I cannot emphasize this enough. You can only use mr squared when it's a point mass or if it's a thin hoop. That's the only time you can use mr squared. Yes?
What's the difference between a thin hoop and a hollow cylinder?
It's just the dimension. You would be told this is what it is. Okay? That's it. You would be told, hey, this is the object and that's the formula that you're going to use. Okay. So, here's the basic idea. So I've got this rod, and I've got two situations. One where the brass weights are at the bottom, and one where the brass weights are at the top, okay? And I want to try and balance this, okay? I want to balance it. So what do I want the angular, when I'm balancing this, what do I want the angular velocity of the end of this rod to be? 0, right? I want that to be at rest, because if it's moving around, that's bad, right? So if I'm going to balance it, basically I'm trying to maintain an angular velocity of 0 at the end. Now, when this thing moves, does every point on here have the same angular velocity in radians per second?
Yes.
Yes. Every point is going to move through a certain number of radians per second. The linear velocity is going to be different. So if you're up there on the end, okay, you're going to be going a lot faster in meters per second than you are down here. So here's my question. In what situation is it going to be easier to balance this rod? With weights at the bottom or with the weights at the top? Okay, those are your obstacles. Bottom, top. So how many think it's going to be easier to balance it with the weights at the bottom? 1, 2, 3. Gaining momentum, so to speak. 3. Okay, weights at the top. Okay. All right, well, you're the official demonstration guy for this class. Come up here. So here's what I want you to do, okay? Put your hand out flat, okay? Got that? And you can take your other hand and try and steady it, okay? So I want you to try and balance that. Okay? Don't take my eye out. Okay, now flip it over and try it. Which one's easier? That one? Oh, that's right, you lost your voice. Oh, hey, I'm sorry. Okay, didn't affect your ability to balance it. So it's much easier. Hold on. That was it, right? It's much easier to balance this thing with weights at the top than it is with weights at the bottom. Okay? And here's the reason why.
More
I equals mr squared, right?
force to move.
So when it's the same mass, right? Same mass. So when I've got that radius way out here on the end, what happens to that moment of inertia? It gets bigger. So with a bigger moment of inertia, that means it's harder to get it to move. Now you can also feel this. If I take this with the weights at the bottom and go back and forth, it's really easy to do that. Okay? It goes back and forth very easily. If I put this weight up here on the end, you can just feel that weight on the end of that, right? It's hard to get it to move, but once it's moving, guess what? Oh, it's hard to get it to stop. Because now you've got all that weight out there that's going, oh, it's moving. Got that idea?
Yes.
Okay, so, ready? Stop that camera. We need to go to the back of the room. Right?
Yep.
The exact same diameter, and they're actually machines, so the mass is the exact same, okay? So, same mass, same diameter, everything. So, I'm gonna put it on this ramp, and what's gonna happen?
It's gonna roll.
It's gonna roll. Is it going to undergo angular acceleration?
Yes.
Yes. So therefore, there has to be a torque that's applied, right? Because if I don't apply a torque, guess what? It doesn't, it's possessed.
You need to reload one too.
Try turning
Really?
it 90 degrees.
No, this is a battle of wills. There it goes. Okay. So if there's no torque, we don't undergo angular acceleration. So what's making it undergo angular acceleration? Gravity, right? Specifically, what component of gravity?
Parallel.
Force parallel, right? So force parallel is making it go down the inclined plane, right? Which would be the same if I set it on its side, same force parallel, right? But if I put it on its side, why doesn't it move?
Friction.
Friction, right? Now, friction is the key to this. So when I put it down here, what if this was the magic frictionless board, and this was the magic frictionless pump?
It would just slide without turning.
It would just slide, it wouldn't spin. Why?
Because there's no friction.
I like that, okay? Because if I'm gonna make it spin, I have to apply a torque, right? So what's creating the torque is the friction between the edge of the puck and the table. That's what's creating the torque, and that's why it's making it spin this way. So you have two factors that are making it roll down the hill. Excuse me, you have the force parallel that's making it roll down the hill, and then you have the friction, which is creating the torque, which is making it spin. Therefore, you get angular acceleration. So here's the deal. I'm going to put these up here like this, okay? And I'm going to let go of them. And we're going to have a race to see which one gets to the bottom first. So here are your options. The solid hockey puck, the Lord of the Rings, or it's just going to be a tie. Because they're the exact same mass, they're the exact same diameter, everything's going to be the same. So here's your three options. Lord of the Rings, hockey puck, tie. So how many vote the Lord of the Rings is going to make it down first? Okay? What about the hockey puck? Nobody's betting on the hockey puck. Okay? How about it's just going to be a tie? Are you on the tie train?
Yeah, sure.
Okay. All right, are you ready? You sure?
Oh, I should have gone. Shit, I hate this already.
Now, here's what I want you to think through, right? Hold on.
I think one side must have a lot more friction than the other.
No, there is, this basically the same. So here's the deal. Look at what affects moment of inertia. Mass and radius. So on this one, on average, that mass is a long way out from the center. Okay? So imagine this is like just what we did, Wall, what you did with that rod, but imagine that you've built a whole bunch of these, where you have a whole bunch of these weights out towards the center. With this one, on average, that weight is right here, because it's a uniform disc. So with this one, it's the same mass. This one, on average, that mass is concentrated halfway out. This one, that mass is further out. So this one is going to have a bigger moment of inertia. So therefore, and we'll switch them up just to make sure it just wasn't one side of the ramp, okay? So now when I let go of this, right? Solid hockey puck wins. So, same torque, has a smaller moment of inertia, you get a bigger fish, okay? Get a bigger angular acceleration. Now, but, what if I got them rolling? which one would roll further?
Probably the
The silver line.
The Lord of the Rings would. Why? Because once you get it going, it would be
It's harder to stop.
harder to stop it. Okay? Everybody cool with that?
Yes.
Now, I have two different containers. Both of these contain 4 ball bearings. Okay? So, put them up here like this. Both contain 4 ball bearings. They're identical. Both contain 4 ball bearings. But now I'm going to let go of it. One of them has the 4 ball bearings located towards the outside. One has 4 ball bearings located towards the inside.
I know
Which one is which?
Inside.
This has the,
Inside.
okay?
Oh, wrong again.
Wow.
Yeah, see, they're inside.
Okay? This one we've got them towards the
Outside.
We should do half and half there.
outside. Okay? So with the one towards the outside, what happens to the moment of inertia?
Increase.
It's bigger, therefore it's harder to get it to accelerate, right? Now we have this one. Okay? So with this one,
It's the anti-gravity
Dude, doesn't cry.
magic.
so this one's been drinking a little bit, okay? So it's been a little bit too many moments in the bar. So what do you think's happened with this one?
Half and half.
Inside.
They're on one side.
With this one, I put all of them on
I'm just dumb.
one side. So what happened there, that's what it allowed it to roll uphill, was because gravity was pulling it down, that center of mass was rocked over center, and that's why it went in that direction. So this might be something from your youth,
That was like
Okay.
It's a big blade.
Give it heads.
okay? Now, what are these called? I bought this on the web.
Beyblade.
Beyblades, right? So first block shame me into buying. This is such an Amazon spur of the moment. Now, but here's the idea. So does this thing have a certain moment of inertia?
Yeah.
Yes.
Yes, because it has mass and it has a radius, right? Now, when I pull on this, what am I applying to the Beyblade?
Or
A torque, right? I'm creating a torque. What's that torque going to create?
angular.
Angular
Acceleration.
angular acceleration, right? So the faster I pull it, what's going to happen to the amount of torque?
Increase.
It's going to increase. So if I do this,
Wait, other way. Other way.
give that back. What do you mean? You got
This thing has to
Show the Beyblade faster how it's done.
Like a top.
turn it upside down and do it the other way.
Hey, I'm not a pro at this.
He almost had
The
it.
Beyblade.
Yeah,
Got the idea.
Okay, so you go like this.
Yeah.
Yeah.
Okay. All right.
Now you need another.
So, does that now have, what have I done to the moment of inertia by making it spin?
Made it big. No.
Nothing.
It did the same.
It's the exact same moment of inertia, whether it's spinning or not. Why?
Because it's
Mass and radius.
Same mass,
Same radius.
same radius, right?
It's-
Now, it has, which we'll get into later, now it has angular momentum, okay? Because angular momentum is because it's spinning. So, here's the deal. To create angular momentum, you have to apply a torque, right? And that torque has to act through a distance, and you create angular momentum. Got it? Good? Grand?
Yes.
Okay,
You
back we
need
go.
another one. And then you need
So we have the solid disk, and we had the Lord of the Rings. Which one had the bigger moment of inertia? Lord of the Rings or the solid disk? Lord of the Rings. So this had the bigger eye. This one had the smaller eye. But which one underwent the bigger angular acceleration? Which one made it down first?
Solid.
Solid disk. So this had a bigger angular acceleration. This had a
Tinier.
smaller angular acceleration. So this is a huge if. If the same torque is applied, here's how you remember this, is that large fish have small eyes. Okay?
I get it.
So here's this big fish, big angular acceleration.
Big fish.
It's going to have a tiny eye. Now, if you like small fish, you could go, small fish have
Bigger.
big eyes. The all-seeing eye. Okay? So I don't care how you think about it, but here's the whole point of this story, is that they're going to be inverse relationships to each other. Okay? Either you have a big fish, a small eye, or you have a small fish with a big eye. And now there's a huge caveat. If the same torque is applied. Now, let's figure out the mathematical side of this. So, with the solid disk, okay, and we're going to use solid disks a lot. So if you look on your equation sheet, the equation for a solid disk is 1/2 mr squared. Okay, this is probably the one that's used the most often. Now, the reason that 1/2 is there is because if you think about it, on average, that mass, because it's a solid disk, on average, like that mass is located halfway between the center and the outside. Whereas if it's a thin hoop, all of that mass is concentrated to the outside, and you can use mr squared. Okay? So, like I said, you will be told in the problem, oh, this is 1/2 mr squared. Okay? Now, with the hoop, with Lord of the Rings, that one you would have to be told these dimensions. So that one we're going to use 1/2 m r1 squared plus r2 squared. And you would have to be told, oh, it's a hollow disk or whatever cylinder, whatever it is.
It's a hoop.
It's a hoop. Okay? So you would be specifically told which one. So basically what's happening on this one, you have R1 and then you have R2. So that's how you know which equation to use. Okay? Which one do you have? Now, notice this is not R1 plus R2 quantity squared. This is R1 squared plus R2 squared. Okay? So if you do, to save some time, if you do all the math, okay, this one has a moment of inertia of 1.8 times 10 to the minus third kilograms meters squared. And if you plug the numbers into here, you get 3.4 times 10 to the minus third kilograms meters squared. Now, here's the problem with moment of inertia, okay? Number one, we don't have moment of inertia sensors, okay? Like if you look at LabQuest, you know, we can measure time. We can measure, you know, when we had when we were doing the magnet lab, and we could use that to measure position as a function of time, velocity, okay? We have force sensors. We can measure force. We can measure length. We can measure time. We have no moment of inertia sensors, okay? They don't exist. But what we can measure is the mass and the radius. So to actually come up with these, typically this is done typically when you take like Calc 3, that's usually when you go through and you derive all these equations, okay, where they come from. So it's actually a function of calculus and taking integrals over different parts. Don't worry about that. So here's what I want you to see. Both of those rings have the exact same mass. So is it possible for two objects with the same mass to have different moments of inertia?
Yes.
Yes, depending upon where that mass is located. But just on the other side of that, you can have two objects that have different masses that have the same moment of inertia, depending upon where that mass is located. So two objects of unequal mass can have the same moment of inertia, but they cannot have the same inertia because mass is only dependent upon, or excuse me, inertia is only dependent upon mass. So, here's the other problem with moment of inertia. You all kind of can get an intuitive feel if I say, hey, something has a mass of 0.2 kilograms. Okay, you all have done enough time in the lab. Oh, 200 grams. Okay, you kind of got an idea of what that is. It's tough to have an intuitive feel to say, oh, hey, you know, the Lord of the Rings had a moment of inertia of 3.4 times 10 to the negative third kilograms meters squared. You're going to be like, okay, cool, right? So it's a mathematical construct, and it works well, but it's tough to get a feel for what that actually means, all right? Okay, now, so, now I want to look at how this plays out. So, here I've got yonder bicycle wheel, right? Does this wheel have a moment of inertia?
Yeah,
Why?
because it has a mass and a radius.
It has mass and a radius, and it has the capacity to spin, right? Now, here's the golden rule when you're making things spin, okay? When you're making things spin, you cannot use F equals ma, okay? And here's the reason why. If I apply a force right here close to the center, that creates a certain amount of torque, and I get a certain angular acceleration. If I apply that same force out on the edge, where there's a lot more torque, because there's a lot bigger radius, I get a completely different angular acceleration. So when something is spinning, you cannot use F equals ma. The only time I can use F equals ma with this bicycle tire is if I'm just going to throw it, okay? So if I'm going to do like Bergkamp's hammer and throw it, oh, I can use F equals ma all day long. Oh, here's a certain force, here's the mass, boom, there's my acceleration. But I can't use F equals ma when I'm talking about making something spin, okay? Cool with this. Now, here's what we're going to look at. I just said you can't use F equals ma, but I'm going to.
Oh,
I know, just chill out. Now, we said from yesterday that torque equals force times radius, right? Okay? Now, even though I just said we can't use ma, I'm going to. And notice that they go, you're such a hypocrite. It's going to be a transition, okay? It's a gateway equation. So what I'm going to do is I'm going to substitute mass times acceleration in for force. Now, you all are flipping out going, Mr. Bergkamp, you can't use ma. Right, you can't. Right, you can't. But from yesterday, what does A equal? What else does A equal in terms of rotational stuff?
Fish.
A equals R fish, right? Okay? So torque also equals mass times R fish times R. Okay? Seems reasonable. Now, so this gets rid of my gets rid of my linear acceleration, and now I end up with angular acceleration. Now, can I write that as mr squared alpha? Seems reasonable, right? Now, what did we just said mr squared equal? Torque also equals I fish. Okay? So, torque at this point equals two things. It equals I fish and it equals force times radius. Now, if this is going to work, what do you know about the units on both sides?
You're gonna cancel out.
Well, they have to be the same,
Yeah.
right? Now, torque was Newton meters, right? Newtons times meters. Well, newtons are the same as what?
kg
Kilograms, meters per
second.
times meters, which gets me
oh,
kilograms meters squared over second squared. Good? Now, moment of inertia, any moment of inertia is measured in what units?
Kg
kilograms.
Meter squared.
Now, alpha is measured in radians per
Radians per second squared. And
second
then
squared.
You can just get rid of the radian.
Radians are this dimensionless number. You get kilograms meters squared over second squared. You get the same thing. Okay? Now, let's revisit the Lord of the Rings versus the disc. So, here's the solid disc. Okay? Here was Lord of the Rings. They both had the same torque applied. It was out at the same radius. It was that same frictional force. Okay? Same torque was applied. So, what do you know about the solid disc? It had a large or small moment of inertia.
Small.
Small moment of inertia, so it ended up with a big angular acceleration. The Lord of the Rings had a
Large.
moment of inertia, so it ended up with a
Smaller initial.
small angular acceleration. Okay? So this is why it works. Okay? So you have to keep in mind torque equals two things. Torque can equal force times radius. It can also equal I alpha. And you have to be able to work both sides of that point. Okay. Cool with that. Got that. Now, here's the next big thing. And that's angular momentum. Okay? Now, angular momentum is L equals I but. Okay? Now, so here's what I want you to look at. And this is kind of cool when you look at like the similarities between the two. So, oh, come back here. So, linear momentum is mass times velocity. Mass is a measure of inertia. Okay, more mass you have, more inertia that you have. So you're multiplying a measure of inertia by how fast you're going. Okay? Angular momentum is your moment of inertia, which is a resistance to a change in angular velocity by how fast you're going. So in both situations, even though they look completely different, you're still multiplying together the same things. You're multiplying a resistance to a change in velocity by how fast you're going. Okay? Makes sense. Now, linear momentum has to be conserved, right? This is why things go in opposite directions. Do you think angular momentum has to be conserved?
Probably.
Let's go with yeah. Okay, so Patrick, come up here. I've used Walt enough. So, Brady, give that a spin. And, well, could you run back and get me a 1 kilogram mass? Okay, you stand on the green spinny thing. Okay, take balance. Hold up. Hold up.
We're gonna make a big
Okay. Now, does Patrick have a moment of inertia?
Yes.
Yes. Why?
Because he has mass.
And he has
radius. Square.
Now, is it possible for him to have angular momentum?
Yes.
What would have to happen?
Movement.
You'd have to spin, right?
Velocity.
He has the moment of inertia part. So here's what I want you to do. What's his angular momentum right now?
0.
0. Why?
Because he has no angular velocity.
He has no spin.
He has no-
Okay? He has no spin. So here's the deal. So here's what I want you to do. I want you to hold these up like this, and then I want you to take the top half of your body and move to the left. Now move back. Spin that around the other way. Okay? Now take your top half and move to your right. Now, as soon as he does that, as soon as he takes the top half of his body and spins to the right, what does the bottom half of his body do?
Going the other way.
It goes in the opposite direction. Why?
Conservation law.
Conservation of angular momentum. Right now, he has no angular momentum, right? So if the top half of his body moves in one direction,
The opposite.
the bottom half has to move in the,
Opposite.
so that the two momentum still add up to 0. So it's just like the exploding carts. Okay, they have to go in opposite directions because he has no momentum to start with. Now, Patrick,
Yeah.
do you think you could change your moment of inertia
Yeah.
by doing what? Okay, so if he takes his arms and puts them out, what has he done to his moment of inertia?
Increased it.
Increase. Same mass, but a
Bigger radius.
bigger radius. So here's what we're going to do. Okay, I'm going to start you spinning. I'm going to apply a torque to you. Okay, I won't do the zip cord thing, which would be really cool. Okay, but
Human Beyblade.
yeah, it would be cool. Like he's like, whoo! Okay, yeah. So I'm going to get you spinning, and I want you your arms out like this. Then after I get you spinning, then I want you to bring your arms in like that.
Okay.
Okay, got it. Okay, don't hit me. You ready?
Yeah.
Balance.
I hope so.
Okay, now bring your arms in. Well, hold on. Do that again. Hold on. We'll do that again. Okay? A little faster. You ready?
Yeah.
Okay, now bring your arms in. Now, as soon as you brought your arms in, what happened?
You were still.
I don't actually know.
Okay, you all are watching him. As soon as he brought his arms in, what did he do?
Oh, raise it so he's still more.
He spun faster, right? Okay, so we'll do this again. This time I want you to put your arms over your head. Okay? I got faith in you.
I'm gonna try not to fall.
I know. Okay, now start with your arms out.
We do need a
Okay.
rope to just tie around him.
Now, put them up over the head.
They keep falling off.
Okay, that's bad. Okay, that's bad. I got this. Okay. So, with his arms out, what happens to the moment of inertia?
It's big.
Big. When he puts them up over his head, the moment of inertia gets
Smaller.
smaller. Well done. Okay. So, here's the deal. If you look at L equals I omega.
Force required to spin.
So, when Patrick had his arms out like this, right? What happened to his moment of inertia? Moment of inertia big, moment of inertia small. Big. So he had a big moment of inertia, but he was spinning
Slowly.
slowly. When he brought his arms in, the moment of inertia became smaller, but we have to conserve angular momentum. So when he decreased that moment of inertia, what had to happen to his rate of spin?
Increased.
Increased. Okay? So when he was like this,
So many things have been learned together.
not a bad stick person, right? So when he put his arms up over his head, then he shrunk that moment of inertia, so he had to spin faster to create the exact same. Okay? All right, Michael, come up here.
Oh, you gotta balance on a bike wheel.
Yeah.
Like a monkey.
Funny. See, where's the accordion?
So we're gonna put you on the green spinny thing.
And the harmonica attached to it.
Got it? Hold the wheel. Okay. Now, what's the total amount of angular momentum right now?
Zero.
0. Okay?
I see.
Now, what I want you to do is I want you to tilt the wheel like this. Feel anything? No? Okay. Now, when you talk about the direction of your angular momentum vector, so what you do is called the right-hand rule. So what you do is you take your hand, your right hand, and you curl it in the direction that the wheel is spinning, okay? So if we're like this, I'm going to curl it like this, and my thumb is going to point in that direction, okay? So the angular momentum vector is going to point out this way. If he was like this, and I spun the wheel in this direction, I would curl my hand like this, the thumb would point upward. If we're like this, and I spin it in this direction, then I'd curl my hand like this, and the momentum vector would point in that direction. So there's two things that are going to determine that angular momentum vector. The direction that the wheel spins and how fast it spins. So if it's just spinning really slowly, that's not much angular momentum, okay? But again, if it's going like this, it's out like this. So I've got a little bit of an angular momentum vector pointing out like this. If it's going much faster, it's still pointing out to the right, but it's a much bigger angular momentum vector, okay? So here's what I'm going to do. I'm going to get this thing spinning really fast, okay? I'm just going to grab it and spin. Then what I want you to do is take that wheel and do that. Okay, you ready? Now you got to stay kind of centered on the green spinny thing, okay? I got faith in your balance. Okay, you ready? Okay, now spin it over. Okay, now roll it all, tilt it like almost sideways. Now tilt it back the other way. Okay, now so go back. Okay, it's pretty cool, right?
Magic.
So it's magic. Now go back. So here's the deal. Whoa. So hold on, let me stop this. Right? Well done. Okay, so why, when he tilted the wheel, what did we change? Did we change the value of the momentum vector, or did we change the direction of the momentum vector? The direction. So Michael had to be part of the system, right? So this is how gyroscopes work in navigations on planes or spaceships. So gyroscopes work by you have a very large spinning mass. So what happened is that when Michael tilted that over, he changed the direction of the momentum vector. So his body then had to compensate for that by spinning in a different direction, okay? Because he changed that, right? When he changed that momentum vector, momentum had to be conserved. So we weren't changing the value of the momentum vector, but we were changing the direction of the momentum vector, okay? And that's why he did that when he was spinning around. Got it? Good? Okay. All right, Brady, stop that for a second. Okay, so on page 201, this is up to the top of this page. So there's on page 201 in your book, there's a whole list of different moments of inertia, different things. And then there's also the equation sheet that I gave you. So those are going to be your two sources for moment of inertia equations. So like on this one, on number one, I tell you a solid disk of mass 1 kilogram has a radius of 0.1, find the moment of inertia. Okay, all you're doing is just finding the moment of inertia, that's it. What's the only time you can use mr squared? Thin hoop or a point mass, okay? That's the only time you can use mr squared. All right, now, so when you get to 5 through 10, so you got a solid cylinder, again you have a solid cylinder, mass of 3 kilograms, radius of 0.5 meters, which is actually fairly big, okay? You consider 3 kilogram mass with 0.5, it's part of a big thing. So I'm going to apply a force of 8 newtons, so imagine that you're grabbing a hold of that wheel and you're spinning it. So, given this information, determine the following: moment of inertia, torque, angular acceleration, all of these things. When you get on the back side, let me paint you a picture of what's happening on number 14. So number 14, you have a a hollow sphere, and I've given you the equation for the hollow sphere, 2/3 mr squared. So it's spinning at 30 revolutions per minute. What are you going to have to do with the revolutions per minute?
Revolutions per second.
You got to change that into radians per second, okay? You have to have radians per second. That omega has to be in radians per second, okay? So you're going to determine the angular momentum of the sphere. So imagine that you've got like this tennis ball and it's spinning like this, okay? Spinning at a constant rate. So then on number 15, a bug is going to come and land on the outside edge of this sphere. And you want to calculate the new rate of spin. Okay? So I tell you, hint, conserve your angular momentum, and the bug you can treat as a point mass using mr squared. So on number 15, here's how you want to set this up. You're going to have the L in the ball plus the L in the bug is going to equal the new L of the ball plus the new L of the bug. Now,
Oh my God.
think this through. The bug is going to land on the sphere, okay? The bug is going to land on the sphere. What two things do you need to calculate L?
Mass.
I and, no,
I and
but.
but.
So this is going to be, this sounds kind of a witchcraft thing. This is going to be the eye of the ball
The butt of the bug.
times the butt of the ball is going to plus the eye of the bug times the butt of the bug. But this is like a California problem. So what do you know about those two omegas?
They go together.
They're going to be the same because the bug is landed on the outside edge of the sphere.
Oh my God.
So it's got to spin slower. So on number 15, you want to calculate the new rate of spin of the sphere. So is that answer to number 15 going to be bigger or smaller than the rate of spin on number 14?
Smaller.
Smaller, because now you have a bigger moment of inertia because now the bug is part of that. When you get to number 16, okay, you're going to determine the angular momentum of the moon as it orbits the Earth. So on number 16, you're going to use I equals mr squared to get the moment of inertia. So you're going to treat the moon as a point mass going around like this. So you're going to use L equals I omega. Now, omega has to be in radians per second. As the moon completes one orbit around the Earth, how many radians does it move through? 2 pi. Now, and that's going to take you 27.3 days. What are you going to have to do for 27.3 days? Change that into seconds. Now, when you get to number 15, okay, you got a solid cylinder, okay, it's rotating at radians per second. I was nice, I already gave you that in radians per second. You're going to apply a torque of 0.04 Newton meters is applied to the outside edge for 5 seconds. By how much does the angular momentum change? So, keeping in mind you're spinning at a constant 3.7, you're going to apply a positive torque, right? So this thing is going to speed up. So you want to calculate that change in that angular momentum. So then you got some problems out of the book to do. On number 35, give the direction, okay, of that momentum vector. Remember the right-hand rule. Take your right hand, curl it in the direction that it's spinning, and then which direction your thumb points tells you the direction of the momentum vector. Okay, I'm done. You're on your own.